Dr. John Jose Nunez is a psychiatrist and clinical research fellow at BC Cancer and UBC Mood Disorders. He completed medical school at UBC and there went on to finish his specialty training in psychiatry and a master's degree in computer science, finishing both last year. His research projects use artificial intelligence and other computer-based methods to help patients with cancer, depression, and bipolar disorder. He and his co-authors recently published a paper in the prestigious JAMA Network Open Medical Journal showing how artificial intelligence can read an oncologist's initial consultation document and predict a patient's survival. He's also using these techniques to help identify which cancer patients would benefit from support for their mental health. In his free time, he likes to travel, bike around the city, and try new recipes that incorporate his favorite ingredient, beans. Sounds delicious. So thank you, Dr. Nunez, for joining us today. And you can now begin your presentation.
Okay, thank you so much for the introduction. I really appreciate it, and for the invitation to be here. It's really neat to see all these people from around the whole country just to come see me talk today. So it's really an honor and really happy to be here. Let me just get this going here. Okay, I think I shared the correct one. Yeah, so I don't need to introduce myself much further. That was pretty much everything. I'm a psychiatrist. I work a bit at BC Cancer and do some AI stuff and all the details that were introduced. So I'll just start off with some quick disclosures that as we like to do for presentations like this. First though, so yeah, my plan today is I'll talk for about 45 minutes to an hour. Kind of depends how fast I start speaking when I get excited, but we'll see how it goes. I do want to say, like, the material is kind of varied in terms of complexity, and some of it, like, it might be like pretty kind of like you kind of need to be a computer scientist or an oncologist or everything else. But I talked around because to people who spoke with y'all before, and they were like, oh no, these folks like know a ton and like know a lot of stuff, so you don't have to worry. Yeah, but you know, if there are parts where like, whoa, what does any of this mean? Super happy to talk a bit about it more. But yeah, like I gave a very similar presentation to the radiation oncologists group of BC last week, so I didn't really change anything. So again, you know, if it's too easy, I'm also happy to go more complicated. So just let me know at the end. Happy to talk about a lot of stuff. And yeah, there also is, I don't know what's going to be sent around, but a Zoom poll, just to ask some questions about your opinions in kind of using AI in medicine and as part of your cancer journey. And I am really excited to hear your thoughts and perceptions about this. Really, you're the first group of you know, potential patients and users of this technology since we've developed it. So this is kind of my first opportunity to actually hear, like, what do people think about this? Are they worried about it? Are they excited? And everything else. So we'll talk about that more. I think we have a whole like hour after the presentation to chat. I need to leave around 1. But yeah, I am really excited and looking forward to just hearing your thoughts and what you think about this all. But okay, so first, yeah, just a quick disclosure. So some of my fellowship funding to do my research came from Pfizer Canada, which is a drug company, but today I'm not talking about any medications or anything like that, so it's not too much of a conflict of interest. And the other thing too is that I'm not a medical or radiation oncologist or a surgeon. I don't treat cancers directly. As a psychiatrist at BC Cancer, you know, I see patients who are having mental health difficulties throughout their cancer journey. You know, sometimes people who already had a mental health condition, and that can complicate treatment, or, you know, somebody who develops mental health, you know, as part of their cancer, you know, because cancer can be, of course, really difficult, and that happens quite often. So, you know, I'm aware of cancer and, you know, have some knowledge of it, but I'm not an oncologist. I'm not a, you know, medical or radiation oncologist. I think that's just important for me to say. Okay, so first to just start with a general kind of idea of what this project is and how it works. We are using artificial intelligence, which I'll just call AI going forward, to read the initial oncologist consultation document. And so that's you know, about 3, 4, I mean, if you're a psychiatrist, it's like 5 pages. It's, you know, if you're a surgeon, it's like 1 page, but like a document that the doctor makes after the first initial consultation appointment. So the first time you see the oncologist, after the appointment, they're going to like pull out their phone usually, and they're going to dictate, again, like a 2-3 page kind of report. And it's going to have a bunch of information in it, like how, what symptoms you're having, what tests you've had so far, what sort of disease you have, what tumor markers are, that sort of stuff. It's all going to kind of be in this document. So the AI is able to read that document and then predict that patient's survival, whether they're going to live 6 months or not, whether they're going to survive 36 months or not, or 60 months or not. And we chose those durations of it randomly. You could choose other times, but those are kind of useful periods of time usually. And of course, it's not like 100% perfect, and I'll talk about the accuracy, but it's relatively good predictions. And yeah, so that's the idea. So we were really lucky to have this paper accepted at one of the JAMA subjournals. So that's a Journal of American Medical Association, which is a pretty well-known journal for medical sort of stuff. And if you'd like to read more or look at the paper, it's open access, so anybody, you could just Google it, just that title right there, and you're able to pick it up and read it. It's not too long, but yeah. Okay, so today here are kind of the kind of objectives. I don't know, it's kind of a silly term. I mean, objective is just to learn about this stuff and see what it's like, and But yeah, so we're kind of going to start by just kind of introducing what artificial intelligence is. We're going to talk specifically about natural language processing, which is the type of AI that could actually read text. Think of course ChatGPT is the big one everybody's talking about. Like Amazon Alexa or Siri, that sort of stuff. That's all NLP, for example. We're going to then talk about why medical documents are a good choice for using these AI predictive models. And then we're going to actually talk about our project itself, using these technologies to make these predictions. Then we're going to actually look at kind of ways we could figure out how the AI is making these predictions, which I think is kind of important, because you want to know if the AI is actually doing something, at least somewhat rational and not doing something like super weird. So we're going to talk about that, which would be kind of cool. And then I'm going to talk again a little bit about, applications, drawbacks, where this is going to go forward. And I hope that'll be a good springboard to have a discussion with you all and see what you think about these sorts of tools. Okay, so let's actually first talk about, again, what AI is and all this sort of stuff. So the idea of artificial intelligence, one of the definitions of it is, the ability to do things that generally require human intelligence. Another way to think about it that I like a little bit more is being able to do tasks without explicit instructions. So normally when we interact with computers, most of the stuff we do, it's all being explicitly programmed. So a good example is if, you're already like, this talk is boring and not relevant. This guy's kind of weird. And you were to click the exit button, right? And then you were to leave, and then you could go enjoy your day or whatever. A programmer has actually sat there, and they have explicitly programmed, if mouse click equals true and position equals, wherever the little button is, then exit program. So that's an explicit instruction. That's mostly how, we program and make computers do stuff. And that works really good. But whenever the computer has to interact with the real world, it's hard to have those like really explicit instructions, right? So one of the first, big applications of AI. Now, AI actually has been around since like the 50s, right? And there's really cool predictions in the 50s, and this is Jetsons came out and all that sort of stuff about how we were going to have robots running everything like by the 60s and stuff. It's really neat to go back and read some of that. But the problem was, like, theoretically they had it all there, but they couldn't. The computers just weren't strong enough to really do anything. So that's why AI is actually now picking up many years later, because finally our computers can actually process this stuff enough. So anyways, one of the first applications of AI was actually for the US Postal Service, and this was back in the 70s, late 70s. And here are some examples of the numbers, and they were just trying to read the zip codes. The Americans just have five numbers they use as a zip code. And you can kind of see that, for us, this is obviously an easy task, but this is actually really hard for a computer to do if you were to try to give it explicit instructions. For example, if you were to tell it, okay, a 0 is really easy, a 0 is just a circle. then you could actually see, well, it's not actually correct. Like this fourth one here, I don't know. Yeah, I don't know if you can see on this cursor, but that's not a complete circle. A person didn't complete it. Some of these are kind of more like squares. If you were to give, if you were looking at like a physician's like numbers, ours are probably even worse than this. There'd be no chance, right? Same with like the 8s, if they're not really like, 2 circles. So there's this kind of like fuzzy, not really quite, perfect aspect of this data. And the Postal Service was able to use artificial intelligence to teach itself kind of what these numbers are and be able to kind of be okay with the kind of the kind of fuzzy nature of this data. So that was kind of one of our good examples. Other good examples of AI is recommenders. So if you watch like Netflix, what show to watch next, they'll remind you. Ads are very AI based. So if you look up shoes and want a website and you go onto Facebook, they're going to show you a bunch of shoes. I mean, some of that's explicit, but there's also AI stuff going in there. Self-driving cars, of course, are a perfect example of AI, right? Because you can't just program the computer to be like, oh, if you see car equals in front of you, do it. No, you can't do it. So you need to be able to kind of think and kind of understand a complex environment. And so that's when you kind of need AI. A big thing people talk about is like, oh, well, recognizing these digits, that's not AI, right? Like AI is like when you have a robot who like C-3PO from Star Wars or whatever. And that's the term we use for that is called general AI. So general AI is when, a robot is able to when a machine can do multiple AI tasks altogether. So, we have things that could walk, we have things that could talk, we have things that could listen, we have things that could see. If you were, to put those all together and it was to work okay together, that would be called general AI. And then we would get like cyborgs or robots or whatever from the movies. And we're not really super close to that yet, but, well, of course we'll see. Okay, so the big question is, okay, if artificial intelligence is the computer being able to kind of do things without explicit instructions, kind of make decisions for itself and understand messy data, how does the AI actually come up with these thoughts, with this understanding? And the primary way to get the AI to have this understanding is to use something called machine learning. So machine learning, and there's a couple other ways to train AI, but machine learning is the big one. So in supervised machine learning, the idea is you're just going to give it lots and lots and lots of labeled training data. So what that means is, I put an example here. So here are 1, 2, 3, 4, 9 handwritten numbers, and you're going to tell the machine, okay, that's actually a 4, that's actually a 5, that's actually a 6, that's actually 0, et cetera, et cetera, et cetera. And as long as it has enough of this data, it's actually able to train and learn and then make its prediction going forward. There's a lot that you go to the philosophy of like, what is intelligence, what is consciousness, right? But this is like pretty similar to how humans learn. I like to say it's very similar to how doctors learn. Like we go to med school for a long time and then residency because it's like, okay, this is what somebody with pneumonia looks like. This is what somebody with depression looks like, right? And it's kind of the same idea. Like our preceptor, the boss doctor will tell us, hey, that was pneumonia. You could tell because the breathing was difficult and blah, blah, blah. So kind of similar to the machine. You give it, here's the messy data, it's this, and then the machine kind of learns. So this is like the most math what we're going to get into. Yeah, I have to be careful around a lot of doctors because math are like, it's just kind of funny, but yeah. So just really quick, like this is kind of how the machine learning actually works. In case you're curious, or you could just take a 2-minute relaxation break here. But generally, the idea is that you're going to have a predictive equation. So that's up at the top. This is just a linear regression model. So just you have coefficients, which are the W's. And then you have the weights, which are the actual value. No, sorry, not the weights. The actual values, which are the X. And you start the weights, the coefficients randomly, and then you're going to define a cost function. So that's just like how good your prediction is versus the real data. And so it's really big if you're getting it wrong, and it's really small if it's getting it correctly. And then you're just going to use a little bit of calculus. So you're going to start at a random guess, and then you're going to look at the derivative, and you're going to use the derivative to adjust all the coefficients to get yourself closer and closer to the bottom here, which is where the error is as low as possible. So yeah, bit of calculus, get the error as low as possible. Eventually, the equations will adjust themselves, and therefore you have machine learning. Okay, so that's kind of generally how AI works. If we want to apply AI to language, then we call that NLP, and natural language processing. It's kind of funny why we call it natural language. You might be wondering, like, what's the natural doing there? The problem is if you talk to programmers and you're like, oh, like what languages can it understand? Then it's going to, like, they're going to think that you're talking about like Java or Python or like JavaScript, like computer languages. So natural language means human language, like English, Italian, blah, blah, blah. So yeah, when we use AI with language, we call it NLP. And the general idea is that at the end of the day, computers only work with ones and zeros. They only work with numbers. So you need to somehow convert the words into numbers, but in a way that makes sense or is possible or actually works somehow and retains meaning, right? You can't just be like, oh, blue is 4 and whale is 2. Like, no, it has to have some idea. So let's talk about the kind of traditional way we used to build these models. And this is something we've been doing for decades now, and it's quite easy to do. It's a technique called bag of words. And the idea is you're just going to get a list of words that you're interested in. That's the bag. And you just count how many times those words occur in a document. And you don't care about the order. You're just saying, is the word present or not? And then you can use those counts to then feed it into a standard machine learning algorithm, because counts are just numbers. So here's just like a really simple little example. It's a bit busy because of all the colors I used, kind of Christmassy for some reason. But okay, so as a simple example, let's say we chose 4 words, which is exercise, work, assistance, and pain. And again, we would usually choose, I think, 500. I think in our models and from our paper it was 5,000. But here we'll just do 4, because otherwise how do I fit that on the screen? And let's say we have these 2 sentences, right? And again, the documents we're using are like full documents, but for these examples, it's a little sentence. So Mr. Joe continues to exercise regularly and continues to work, and Mr. Bob is having assistance at home and lots of pain. So if you were to just kind of guess, which of these patients would be likely to survive, less likely to survive, you might think the first one, it would be a bit more likely. The second one would be a little less. Of course, just because you have pain or you're getting assistance at home, that doesn't mean you're not going to survive your cancer at all. But like these things would just make you guess, one way or the other. Yeah. So I don't want to worry you if you've had pain. It doesn't necessarily mean anything. But this, again, just an example. Exercise is always a pretty good thing, right? It always helps us, but it can of course be difficult in the cancer journey. Okay, so you would convert these sentences to these little vectors. Vectors are just a little list of numbers. So the first one would be 1100, the second one would be 0011. And then you could imagine that you could use a kind of simple formula, something like here at the bottom, where and so maybe this is predicting that, or you want it to produce like the percentage chance of the patient surviving 6 months. And you could start with, it's like 50 plus 30 plus 50 minus 60 minus 40, and you can kind of see that the first one, it would be 50 plus 30 plus 50, so that equals 130% chance. Of course, 130% chance of survival, that's kind of silly, but it doesn't really matter. That the algorithm will just be like, okay, if it's above 50%, predict the patient lives. And the second one would be 50 minus 60 minus 40, and that would be minus 50%. And again, that doesn't really make sense, but as long as it's below 50, the computer will just predict the person doesn't survive. Yeah, and so the bottom here is what's actually being learned is these weights, right? Because these numbers would kind of make sense as a guess, but of course we don't actually know them, and the coefficients, numbers in front, are going to be random at the beginning. So you're going to give it training data, and the algorithm is going to adjust these coefficients, these weights, and so eventually you might end up with something like 30, 50, negative 60, negative 40, and then you have your predictive model. Yeah, so happy to talk about this more. Of course, it is kind of hard to perhaps wrap your head around. I mean, I took like whole courses in this, right? So it's hard to explain it in a few minutes, but it's kind of the general idea. Yeah. Okay, so that was the kind of traditional way to make these predictions, right? And again, for a lot of tasks, it works well, but the language can be much more complex. And so you could have a sentence like, John Jose eats candy all day and does not exercise, which I don't know, it's maybe true, maybe not. I won't say much more. But you could see that the sentence actually has the word exercise in it. So if you think back to our prediction, the person would be expected to have high survival, even though it actually does not exercise. So that's a bit of a problem. So the question becomes, how can we have more complicated understandings of language, understand things like negations, or you can have much more complicated, right? The oncologist could write, the patient does not like to exercise, or the patient is not able to, right? So it doesn't have to be like not right beside it. Like you could have lots of different language constructs. So the idea was to use what are called neural networks. And if you've heard of deep learning or neural networks, they're all kind of the same thing. It's a big kind of buzz thing today. Again, invented many, many years ago, but only now can we actually fit them onto a computer. So that's why they're becoming useful. And then barely now we can fit them on computers. It's still like you need pretty powerful hardware and stuff, which is kind of cool, right? And yeah, they're roughly modeled on how the brain works. If you think of, or if you kind of look at a function like this, the idea is that instead of just like this is just like a linear regression, you're going to have like linear regressions of linear regressions of linear regressions of linear regressions. So that's what these little circles mean. It means that you're doing like combinations of combinations of combinations of your data. And because you can make these like fancy combinations, you can actually get fancy predictions. So I'm going to give you some examples. But one of the things that these rely on is interpreting each word as a list of numbers. So one word might be like all these numbers, and another word might be another bunch of numbers, but somehow this actually has meaning. So how this works, and don't worry, if I'll be getting on to the actual cool part of the project soon. So just a few more slides. But how this works is you're gonna start with just random numbers for all your words, and then you could do something called a skipgram model. So the idea is that if you had a sentence like the quick brown fox or the lazy dog, for fox, you're going to use it to predict the word before it or after it, doesn't really matter. So for instance, you might want to predict, what word comes before fox. If you hide brown from the model, and what word should go there, and then you'll ask it. And if it predicts brown, then you're like, yeah, that's great. And if it doesn't predict brown, then you're going to adjust fox's vector, its number, to be a bit more similar to brown. And when you do this billions of times, and when you do it over like all of Wikipedia or like all of Google News or like every written thing on the internet, essentially, you'll eventually get really good understandings of these vectors. These numbers will actually start to represent things, because again, there's so many numbers that they can kind of store lots of data, and they'll kind of be able to have a neat understanding. So an example of this is with these vectors, with just math, you're able to do stuff like, if I say to you, king is to queen as woman is to what, you're all going to be like, man. And, you can actually do this just algebraically. You could say king minus queen plus woman equals what? Man. And yeah, there used to be a little website I could show you, but the website doesn't work anymore, which is annoying. But yeah, again, like it's just kind of math, right? It just with the algebra, because vectors are points and spaces, blah, 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 blah. So anyways, the idea is that because you now can store words as like a big long list of numbers that has meaning, you could then get it to do fancier tasks. So, if all it could do is this king to queen, woman to man thing, that wouldn't be that useful. But you could then get it to do, interesting things like, turn off your lights in your room if you're using Amazon Alexa, or in our case, make these survival predictions.
Sure.
Oops, sorry, that was my Alexa. Okay, so in our model, or in our project, we use a few different models using these technologies. And again, I'll just kind of give an overview of them. So again, these are the neural network models. So one of them is called CNNs, convolutional neural networks. And the idea is that these ones break your document down into little clusters called convolutions. And then they look at the combinations of these clusters, and usually combinations of the clusters. And so this allows it to kind of do cool stuff. For example, it allows it to understand that does not exercise is completely different, potentially, than does exercise or is not able to exercise. So those combinations could all be different little convolutions, and the model could learn that those convolutions have different meaning. So then you could make a better prediction. Another model we use is called recurrent neural networks, RNNs, which we use something called long short-term memory, which is a type of. And the idea how these ones work is they read the document one word at a time, and at each word they update the prediction, but they're able to remember what words they've read, a few words ago or even longer past ago. So if they read like denies, then they read shortness of breath, then they'll be able to read, okay, wait a sec, shortness of breath is bad, but if you said denies 3 words ago, then it's probably fine. And so that's how they'll be able to read, whole document. Lastly, we have the large language models, and these are, things like, again, ChatGPT and GPT-3 and 4 and all that sort of stuff. In our work, we did use one of these. We used one called BERT, which was what was kind of just before the GPTs. Because we started this about 4 or 5 years ago, this project. So BERT wasn't quite out, or the GPT-3 and 4 weren't quite out yet. But yeah, and the idea of these, very related to kind of what we were just talking about, but essentially they train, instead of just the vector for each word, they train the entire model on just gigantic amounts of data, so like all of Google News and all that sort of stuff, just billions and billions of words, to do a really simple task. They use it to just here's a sentence, pretend this word doesn't exist, what word should fit there, and then that's how it trains over and over and over again. I'll just keep doing that for, again, lots of documents. At the end of it, you get this big neural network model that has this like good understanding of language, because it's able to detect what words should come next. And what you could then do is you could fine tune it, so you could then get it to make like a prediction of other things that you want. So for example, in ChatGPT, initially it was just trained to tell you what word is missing, and then they fine-tuned it to then answer questions, and you could do that and then get it to do cool stuff. So we took our BERT model and we fine-tuned it to make these cancer predictions. Okay, so that was a brief introduction to AI and NLP. Again, super happy to answer questions, to go way more into depth or kind of more of an overview. Happy to. Okay, so the next question is, why are we trying to predict survival from these text documents, right? You might have wondered, like, that's kind of a weird thing to use. And computers pretty much can predict anything from anything, right? The question is that if it's not useful data, just the predictions will be very low quality, very inaccurate, right? So you need to find stuff that's actually relevant, right? So if you want Netflix to tell you what movie to watch next, it's going to use what movies you've watched in the past. It's not going to use like your shopping history off Amazon or something. That's not going to be very relevant. So in cancer work, a lot of previous work has been using genetic data to make these predictions. So they'll look at the genetic markers from the tumors. Or they'll do stuff like based on imaging. So, here's a brain scan here, but CTs or PETs or everything else. Or just using like medical information about somebody's illness. They'll put that into the AI model, and then they'll make the prediction from there. And we call all that sort of data structured data, because it needs quite a lot of processing to get it ready for the machine learning model. The problem with this approach that we're kind of addressing in our paper is that every cancer agency out there is going to store this data slightly differently. It's going to, for instance, one cancer agency, maybe whether you smoke or not is an important predictor for cancer survival, right? One cancer agency might collect that information and store it in a nice spreadsheet, one might not. And then what do? If you have one model that uses that, but the other one doesn't, then you're kind of out of luck, right? So the idea about using the consultation document is that pretty much anywhere, in the English-speaking world, if somebody's being treated for cancer, they're going to have one of these documents, and they can be pretty similar. So this theoretically allows us to use these models, that we trained BC Cancer Data to use them anywhere in the world. And this has a lot of advantages, one of them just being that the more training data we can provide, the more patients the AI can see, the better it's going to be at its task. So yeah, that's why we use these documents. Okay, so now we'll actually talk about the project. That was a pretty long introduction, so excited to actually talk about what we did. So we'll first talk about the data. So we have our data set is actually over a 50,000 patient database, which does make it one of the biggest data sets in the world. And this is really what allowed us to make this project actually work, because as I was kind of saying before, you need to give these models lots of data to train, or else they're not going to be able to learn. It's kind of like if you only allowed a med student to see 5 patients and then they graduated to become a doctor, they would not be a very good doctor. So you need to give them thousands and thousands, and it's the same thing with these models. So we're using pretty much all cancer patients' data that started their cancer journey between 2011 and 2016. We had some exclusions, like if somebody had multiple cancers, then we excluded that just because it would be too hard to kind of know, which cancer the patient died from, if they did, et cetera, et cetera. And again, we use the initial oncologist consultation document. And this is kind of just a little example of what they look like. I'll show some other ones in the future, but it's kind of doctor speak and just text and just has a bunch of information. So again, kind of talked about this a bit before. So what are we actually predicting? We predicted 3 different things: whether a patient will survive 6 months, yes or no; 36 months, yes or no; or 60 months, yes or no. So again, you actually could just choose any numbers you wanted. We just chose these because 60 months is 5 years, and that's a common thing used in cancer survival work. 6 months is shorter, and so on and so forth. You could also actually use it to predict the specific number of months a patient would be predicted to survive to. But there's kind of a couple of reasons why it's just logistically a bit harder to do that, and it's harder to judge the accuracy of the model, for example. And when you're presenting scientific work, it's nice to have a kind of clear, this is how accurate our model is, for example. Okay, so yeah, why are we actually doing this? It is a great question, right? And research is sometimes figuring out the tool before you know the question you're answering, right? I mean, there are obvious things that this potentially could be used for, but I think that some of the next steps are really going to be how can this be used for? Is it useful, right? The big idea is that we're making personalized predictions. So predictions for the individual patient in front of us. Throughout your cancer journey, you might have at some point had your oncologist say, you have a 90 with this stage and this type of prostate cancer, you might have a 90+% chance to survive in the next 5 years. And often these numbers are useful and they're good, but everybody comes very differently, right? Some people could be older than the average, some people could be younger than the average, some people could have a lot of medical other illnesses, comorbidities that might make the survival more difficult. Somebody could be younger and much healthy and etc. So the idea of this is that instead of those population level statistics, it allows a very personalized prediction for just that person in front of you, right? So yeah, it might be helpful for things like, when you want a more aggressive chemotherapy added on to your radiotherapy, or do you want to have a less aggressive therapy, that it might help with that. And maybe it kind of helps. We'll talk about it a bit more later, but kind of solidify or back up what the oncologist is saying. But yeah, we're really quite curious to hear about your thoughts about whether this is even something you'd want to use at all. Maybe you don't. Maybe this is I'd rather not learn about what's next. I'd rather just see how things go and not use a tool like this. And then that's completely open to that too, right? 100%. Okay, so a few more things. This is a bit more of a computer sciencey thing, but it's a really important thing whenever somebody wants to sell you or tell you about an AI application, which is something called external validity. And the idea is that AI models, when you give it the training data, can be really good at learning that training data, but then actually be really bad when you give it new, fresh data in the wild, right? The kind of med school equivalent would be like, if you're really good at seeing patients, if you have your preceptor, hanging over you, that if you go out in the world and graduate, then all of a sudden you're like panic, right? That it's not going to work. And similarly with these machine learning models. So there's something called external validation, which is when you train your models on one set of data, and then you evaluate them on a completely unrelated new set of data. And that establishes external validity, external validation, and tells you this model is actually doing something. So yeah, we weren't able to do that for this project because it's there's of course tons and tons of very strict privacy regulations about accessing data like this. Happy to talk about that more too, of course. And so we couldn't like go to Alberta easily and be like, hey, can we see some of your cancer patient documents? We're planning to now, and hopefully we'll soon, but hasn't been yet. So what we actually did is we took 20% of the patients. We kind of put them aside, we built everything, got everything ready, and then right at the end, we evaluated them on this 20%, what's called a holdout set, to make sure they actually were doing something useful. Okay, so here we could compare the result, or this just kind of shows the results of how this is working. So yeah, these are all kind of weird metrics that we use for predictive models. So on the leftmost column, you can see the different models we were using. Again, the BOW is bag of words. That's a traditional NLP method. CNN and LSTM are kind of standard neural networks that we used. And then BERT is an example of a large language model, which is kind of all the rage recently. And you can see the accuracies are about 83%. The next one is called a balanced accuracy. Balanced accuracy is when you weigh predicting people who will not survive and people who will survive evenly. Just because if you have like a data set of like where 90% of people survive, and you could just predict everybody survives, and you'll be 90% accurate. Then the balanced accuracy will only be 50%. So that's what balanced accuracy is. And the other numbers are the numbers that we just learned. So yeah, my kind of interpretation is this is pretty good. The kind of joke I like to make is that these are like roughly the marks you need to get into med school if you're at UBC. So maybe the model could get into med school, but maybe not. But at least when I was applying to med school, this was quite a few years ago now, so it's probably higher. But yeah, it does seem to work somewhat well. Interestingly, so now this shows the results of predicting the 6-month survival versus the 36-month survival versus the 60-month survival with our two best models. And you see it's actually quite a bit easier for the 6-month survival prediction, and the accuracy there is actually about 85%. So and then it's a little bit lower for the 36-month survival, and then a little bit lower still for the 60-month survival. That kind of makes sense. It's kind of like predicting the weather, right? The weather predictions are usually pretty good for later today or tomorrow, but for next week they're going to be a bit less accurate. Okay. So that was kind of the project and how it worked. But next, I just want to talk a bit about actually trying to understand our models and like how are they coming up with these predictions? What are they actually looking at? Are they just being really silly and looking at completely ridiculous things that that's just a weird artifact or yeah. So we want to know what they're actually doing, and it's useful again kind of for quality control, right? To make sure it's doing useful things. But also another way is it can actually be used for research, because we might come across things that are like, oh, wow. So if a document has a certain word that actually impacts survival a lot, it doesn't mean that it's causative. It might just be a correlation. It could just be a coincidence that these things are related, but it could kind of lead to investigations of oh, maybe we should look at maybe I don't know what a good example is. Well, I'll show you the next has some of them, but it can also be used to kind of suggest next research topics or things to look at. For the neural networks, though, it can be quite difficult to interpret them. They're often called black boxes because there's no way for researchers to access them because they can be so complicated. They're just these like massive, many layers of layers and layers and layers of combinations and words and all this sort of stuff. And it can actually be like, difficult to understand them. So I'll show you a method that we use to kind of understand them a bit, which is kind of cool. Yeah. So this is the bag of words model. Again, the traditional one that just counts the number of words and then puts these into a formula. So these are the 10 most important words for making the predictions. Apologies if anybody has color blindness, that would probably be a bit harder to tell, but yeah, you can see that palliate, and I should say, so these are called stems. So when we do this modeling, what we'll do is palliative and palliation will become palliate and just become the same word. And this just kind of helps the results be a bit more accurate, because if a word has like a lot of very similar words, you just want to combine those one thing. So yeah, so palliate, unsurprisingly, was the number one word, because if the oncologist writes in their document, we should refer to palliative care, it may mean, on average, that the patient has less chance of surviving either 6 or 60 months. Again, not always, palliative care could be used for people who are going to survive the rest of their life, but just have a lot of pain, and it's a great service. But unsurprisingly, that was our number one. And then you can kind of see interesting things, kind of differences between the 6 months and the 60 months. For example, there we go. So prostate, I guess, but probably prostatic or prostate was a positive predictor. So if somebody has prostate cancer, they're generally going to be thought to survive at least the 6 months, according to this model. Similarly with breast cancer, that's one that also has usually pretty good survival. If it says hospit, that probably means hospital or hospitalization, and that's a bad predictor, unsurprisingly. And unfortunately, it's a negative predictor of static, of course. Some interesting stuff too, though. The word no is kind of interesting. But you have to remember that it's the count, not just whether the word's present. So probably like if it's 20 no's, then that's probably predictive, right? But maybe 1 or 2 no's probably isn't too much. And there's some interesting stuff like white horse without the E for some reason. I don't know why I cut off the E, but so people who are in white horse have a better chance of surviving 60 months, which is kind of interesting. And this is a good example of like how this could actually spur research, right? Probably it's that people who are being treated in white horse have less acute cancers, because if they do have a really aggressive cancer, often they'll have to, we'll have to find them a place to live in Vancouver for treatment or something like that. So that's probably why if somebody's living in white horse, they're also quite young up there too. That's probably another factor, is that the population is generally quite young in white horse. But yeah, so it could be something cool to look into. Okay, so here are how we could interpret the neural networks. Again, we're using something called integrated gradients. And the idea here is it shows one document at a time what the neural network is thinking. So what I did here is I created a fake document, of course, because I'm not going to put real patient data on a presentation. But it's like pretty similar to I kind of took like a couple real ones and looked at them, and then like kind of mixed and matched and changed like a bunch of stuff. So it's more or less kind of what you'd expect in these documents. Okay, so there's a red shading for things that the AI thinks is a negative predictor for survival, and where green means a positive predictor. So I hope it's big enough. It is a bit small, but you can see in this first one, this is the start of the document, and it says Joseph is an 83-year-old male who presented to the emergency with hematochezia. So that is blood in the stool. Blood when you go to the bathroom. And you can see that for 60-month predictions, being 83 years old was a negative predictor. And that's very understandable, right? Even if you don't have cancer at 83, your chance of surviving another 5 years is going to be lower than the average, which is very relevant if you follow American politics right now, but won't go there further. But for 60 months, interestingly, the age is actually not that relevant. And that kind of makes sense too, right? Like there probably other things are going to be more relevant for the next 6 months, like what type of cancer you have, etc., than particularly your age. Here's another one. So this is kind of in the middle-ish of the document. It's kind of talking about the patient's function at home. So, it talks about him using a walker and some oxygen when they exert themselves. And we see a little bit of a difference, which is interesting. For the 60-month, the fact that somebody's using a walker is a negative predictor again. And that again can make sense. In the long term, somebody might not survive if they're using a walker. Not always, of course, but possibly. Whereas the 6 months prediction didn't care about the walker and instead cared about the ECOG status, which is ECOG is an oncologist might have brought it up with you. It's like how a person's current functions, like whether they're working or if they're doing like chores at home, or if they're kind of just able to do a little bit, or if they're kind of mostly bedbound, that has like the different ECOG statuses. So that was more relevant for the 6 months. Okay, of course, the actual disease itself is really important for these predictions. So this is a part of the document where they're talking about the pathology results. So muscular propria is the layer of the intestine where this is a colon cancer patient, so where the cancer is. And there's the whether the cancer is spread through the lymph nodes or through the blood vessels. There's the resection margins, which when you do the surgery, is there a disease left over, that sort of stuff. And you see that both of these are green. It's a little hard to see on the screen, but for 60-month, it's a little less important, some of these disease statuses. And for the 6 month, it's more important. They're a bit darker shaded. And the reason is probably because again, for the 5-year prediction, it's not only the patient's cancer, but also everything else going on in their lives, whether they have had high blood pressure and that sort of stuff, probably, right? But for the 6 months, what's really important is what type of cancer does this patient have right now, because some are going to be a lot more aggressive than others. Yeah, and we kind of can see that a bit. So here's a section that just talks about those medical comorbidities. And for example, this patient has Barrett's esophagus, which is also esophagus disease, and so having that it is quite a negative predictor of surviving the 5 years, which is interesting. Similarly, with having some congestive heart failure, so that's heart problems, and again a reason why somebody might not survive 5 years. But on the contrary, the 6 months prediction didn't really care about that stuff too much. Cared about something called a MIBI test, which is a heart test, and that's kind of interesting. I don't know why it looked at that. And these models are going to think of some stuff that's kind of weird. You just want to kind of generally see that they're doing kind of appropriate things. And I think in this situation, I think a lot of these do make a lot of sense. Okay, so getting close-ish to the end. So again, thank you. This is a lot of stuff to go through. I really appreciate your attendance today, but I'll just talk about kind of what our interpretation of what we're kind of thinking about these results and some of our next steps. So again, as we said before, this is the first time that the first work that people have used NLP to predict cancer patient survival off of just the cancer document without any other data. Like we don't tell the machine like age, we don't tell it type of cancer, that we tell it nothing. We just give it the document. And nobody's really done that before. There's like some stuff people have done with using a little bit of the document combined with other data, blah, blah, blah. But this was like the first, just the document. And again, we're using a document that's like really common, that most people are sort of probably going to have some document that looks kind of like this. We don't really process it much. We just like pick up punctuation and stuff like that, but it's kind of there. And the performance is pretty good, right? People often say that we need to get 90% accuracy in order to use something clinically, and perhaps that's true, but we're at the kind of 83 to 85% range. So that's getting pretty close, and perhaps with some further development and further advancements, we could get up to the 90% point. Okay, so there are a couple kind of limitations or like things, of course, to be aware of. The big question is like, why can't you just use the population level numbers? I kind of talked about this briefly, right? Because we know that like, lung cancer stage 4, your chance of surviving 5 years is 20%, this blah, blah, blah. But again, the point of this is to make individualized predictions for the person in front of you instead of the population at large. The models, though, they might be just kind of learning these population level statistics, which is kind of interesting. So the question is, how personalized are these predictions? And that'll be something that we'll be looking at a bit more. One of the interesting things, and this actually often happens in NLP, is that the neural models, the fancy new technology, actually didn't outperform the old bag of words technology. which suggests, at least to the extent that we tried, the fancy ordering of the words, the complex language doesn't really matter that much, as opposed to just what words are present in a document, right? And perhaps that makes a lot of sense. Like if it doesn't really matter where the person puts palliative care, palliation, if that's anywhere, it's probably going to be a somewhat negative predictor. Same with metastatic. It doesn't really matter what the sentence looked like that it was in, perhaps. So it was an interesting result. And interestingly different than, I'll talk about it really quick, but we have another project looking at predicting what patients need to see a psychiatrist. And in that case, the neural networks were useful. So they're like a more complex understanding of the language, and what the oncologist is writing actually is helpful to make the predictions. So kind of an interesting thing. The LLM, the BERT model, again, the kind of chat GPT sort of thing, actually was our worst performer, which is interesting. And kind of shows you that, like, just because something is good for, helping you cheat on homework or whatever else people are using chat GPT for these days, doesn't mean it's going to be good for everything else, right? When you take a look at things. One of the reasons probably is that BERT, and I think ChatGPT, they can't read that long of a document. They can only read like 500 words-ish. So if you can only read half the document, you probably can't do that kind of a job, and that might be some of what happened there. Yeah, sorry. And I briefly talked about the external validation, and I just do want to bring it up again. Like we don't really know how well these models will predict, on new patients until we really could test it on a completely new data set. So it would be great to, Princess Margaret out in Toronto or Alberta or the States, and we're reaching out to some folks to try to make that happen. And even if the performance is less, it's actually not necessarily too bad. Because there's different things we could do. We could actually take our models, take our AI here, and then let's say we're predicting that, in Edmonton at Alberta Cancer Services, we would then give it a little bit of Alberta data. It would help it fine tune, and then it might become just as good at looking at the Alberta data. So there are kind of cool things you can do. Because like for example, Whitehorse was a helpful predictor, but Whitehorse isn't be relevant anywhere besides BC. So anyways, just something for us to look into, and it will be important. And of course, there's like lots of other things we're going to be doing in the future. So we're going to be looking at predicting the survival of specific cancer sites. So our project, I don't know if I actually said this earlier, sorry. We're looking at all cancer patients, essentially, right? It doesn't matter what type of cancer you have. Our prediction was working on. We used it. But next, we're going to be doing like specific predictions for specific types of cancer. So lung cancer, prostate cancer, colon cancer, etc., and see if those are any better if they're made to be specific, or if they're kind of just as good generally like our current ones. And then a big thing is, of course, understanding if and how clinicians and patients actually want to use this technology. Is this going to be helpful, or is this kind of just it's a cool technology, but something that's not actually going to affect anything or be useful? And then there's also some cool stuff. There actually has been some previous work comparing AI predictions to oncologist predictions. So if you actually get the oncologist to sit there and predict, seeing who wins, the computer or the oncologist. So it would be cool to do that with our stuff and see if it's any better or not. Yeah, the previous work does give the AI usually a little bit of an advantage, which is interesting to think about, right? But not gigantic. So it is kind of interesting. Yeah, so I have all those Zoom questions that I don't know when they were sent out. If they'll be sent out like maybe when I finish this presentation we can send it out. I'm not sure, but the kind of general things that, as I brought up, that I would be really curious about your thoughts about, would a personal prediction for you have been useful right at the start of your cancer journey? Would you have wanted the AI to tell you what your chances of survival are? Is there any way we could kind of make this more helpful, or is there like something in particular you would have wanted to have known? What concerns do you have for it? Right, there's a lot of potential reasons to be worried about using AI, and what concerns do you have about it? One of the things that a lot of literature talks about is that being able to interpret the models and figure out what the model's thinking is really important for doctors. Do patients care about that? Do patients want to know, oh, well, the fact that the AI read that you have type 2 diabetes, and that's why they think your survival chance is lower. is something like that useful, or do you not really care what the AI is thinking? And are there other things that you would like the AI to predict, right? We're predicting cancer here, but it could predict, kind of anything really. As an example, what my other project, and one of the answers of why is a psychiatrist predicting cancer patient survival, it's kind of weird, is the other kind of similar project that we also have, we submitted to a scientific journal or not, is predicting what cancer patients will need to see a psychiatrist or a counselor. The idea being that, sometimes people don't know about those resources there. Sometimes the oncologists don't really think about it. So if we could predict, who should see a psychiatrist or counselor, it might be helpful, and we might be able to refer patients to these resources a bit sooner rather than later, because it's often helpful to treat things before they get too bad. So that's one example of what else we could predict. But yeah, it would be really great to hear what else you think, and other things that might be helpful to predict. Okay, so that's pretty much the end of my presentation. I'll just really quickly run through all the people I have to thank, because this is being like a big 4 or 5 year project, and just so many people help. So my co-authors, Dr. Cheryl Ho, she's a medical oncologist at BC Cancer, Bonnie Lung, who's an MP at BC Cancer, Alan Bates, who's another cancer psychiatrist, the head of cancer psychiatry at BC Cancer, and then Raymond Ng, who's the professor at UBC Computer Science, who was one of my supervisors for my thesis. And then, of course, BC Cancer and the PHSA data stewards, just to make sure everything was done really safely, and making sure confidentiality and privacy, of course. So these people were super helpful. Computer Science and Psychiatry for letting me do this project during residency, which was a lot of fun. And then, we were able to get funding for this to support me doing this work from the BC Cancer Foundation, and also the UBC Institute of Mental Health through the Marshall Fellowship, which I really appreciate. And of course, I'm just super thankful for all the data for all these like 50,000 cancer patients. Every on my data, it's just a little each person is just this little row on an Excel sheet, right? But every row represents a real person who has a complete unique life and their own journey through cancer, which of course can be really difficult, and I just feel really privileged to be able to use this data and really appreciate it. So yeah, big thanks to you all. Really thank you for listening to the presentation, and look forward to the discussion. Yeah, this is kind of funny, but halfway through halfway through this project, over 4 or 5 years, my father developed colon cancer. So all of a sudden, this project became a lot more personal, right? But yeah, so I do have both like a personal and professional understanding of what the cancer journey is like, and just wish you all to do the best, and thank you for your interest in advocacy, and I know the journey could be really tough, and so my thoughts are definitely with you all.